Of thermodynamics applications. First of all, I want to set the office hours, which is Thursdays 11:30 a.m. to 1 p.m. if you all agree with this. And also anytime you have any question regarding the course, assignments, lectures, anything, let me know by an email in advance and I will set up a time to answer your questions. And again, my office is ACE 3030B. In the third floor of ACE building. So today, from this tutorial, every tutorial we're gonna solve one or two questions regarding your lectures and some kind of problems that we discussed, and also we go into details and the concept and everything. Today it's a two-stage Brayton cycle. So you had a simple Brayton cycle in the last tutorial as I explained. Here we have two stages of compression and two stages of expansion. So question, as you see, it's in the thermodynamics channel book. I think ninth chapter, question 108. So it is posted in the Blackboard, so you can access this and also the solution. So consider an ideal gas turbine cycle with two stages of compression and two stages of expansion. The pressure ratio across each stage of the compressor and turbine is 3, means that the air is compressed in the first stage 3 times and then again 3 times in the second stage, and air enters each stage of the compressor at 300 Kelvin and each stage of turbine at 1200 Kelvin. Determine the back work ratio. So this is a definition that we need to know: back work ratio and thermal efficiency of the cycle, assuming A, no regenerator is used, and B, a regenerator with 75% effectiveness is used. So effectiveness, also the third term that we have to know the definition. So back work ratio, thermal efficiency, and effectiveness. And you know, regeneration is basically a heat recovery within our system for better efficiency, which I will explain to you. So first, let's go to the schematic of the system and some assumptions that we have. The assumptions are usually in every thermodynamic problems that you have as a cycle or a system, you have steady state operating condition. Means that the properties of the substance remains constant throughout the system. And second, the air standard assumptions are applicable. Air standard assumptions, because it says that it's an ideal gas turbine, and here air standard assumptions means that you can go to the air table at the end of your book. And kinetic and potential energy changes are negligible, which means you had the energy balance equations as this is the general form, E So in this general form, you have this 0, 0. Basically, these are not 0, but the deduction comes as 0, so means that you are dealing just with H in energy balance equation. And for the case of regeneration, regenerator's effectiveness is 75%. So let's first go to this case, which is without generation. So you see from the state points 1 to 8, and here we start. So basically, for any of these kind of systems, first we begin with the known properties that we have for any state of the cycle. So if you look at the cycle, we have the T1 equals 300 Kelvin. And so basically we have noun properties for 1, 5, and also the compression ratio of 3, and effectiveness of 75% for the case of regeneration. So first, begin with the state 1. So we have T1, 300 Kelvin. So because the air is ideal gas and we have the air standard table, we can find the properties like H, enthalpy and entropy of the air through just temperature. So we have temperature of 300 Kelvin, so we have the H 1. So can somebody of you open the solution? I forgot the paper. Open the solution and just give me the numbers. So basically H1, it's the numbers, and like for H step.
We did this one in class actually.
Oh, you have that? Or?
Yeah.
Okay, thanks. No, okay. Yeah, thanks. So we have H1 as 300.19 kilojoule per kilogram. And we have PR1 from the table as 1.386. So we have PR1, which is the standardized basically pressure for ideal gases, and we have H1. So we want to know the properties of 2. So we go step by step. So we have this pressure ratio definition. P2 over P1 equals PR2 over PR1. So we have this as 3, right? So we can say that PR2 equals 3 times PR1, which is 4.158. So we have PR2. We again go to air table. And from here, we find H2 as 411.26 kilojoule per kilogram. So there is one thing here, because we have this equal compression ratio. So basically, we begin with 1 and going to 2, and then 3 has the equal temperature as 1. You see, in the question, we have each stage of compressor at 300 Kelvin. And because the compression ratio is the same, and it's air, so that at the end of each compression ratio, also the temperatures of this are the same. So you see here, 1 and 3 are in the same constant temperature line, and 2 and 4 are in the other constant temperature line. Basically means that H2 equals H4 in this case, and H1 equals H3. This is the case just for the case of ideal Brayton cycle, where the compression ratios are equal. So you see, ideal means that we have isentropic compression from 1 to 2. You see just a vertical line, which S is constant. In the ideal form, we have, in the real form, we have like this, a line like this, which is 2 actual, and 3 to 4 like this. But here, we have an ideal Brayton cycle, means that the processes in turbine and compressors are isentropic. So in the case of ideal cycle and the case of the same compression ratio, we can write H2 equals H4 and H1 equals H3. And the same for 5 and 7 and 6 and 8. So basically this equals H4 and H3. So we have 1, 2, 3, and 4. So one important thing in these cycles that we go step by step to find H. H's are the key to find out the work of compressors, the thermal efficiency, and all those things, because H comes as energy balance equation, into energy balance equation, and from energy balance equation we can find out the work, the heat, and also the thermal efficiency for the whole cycle. So the H you can, like in your exam, in your assignments, just draw a line around it and put it in a box, something like that, make it easier for us. So we have H1 to 4, and 4 to 5 we have combustion chamber where Qin coming from fuel. So fuel is burned there and gives some heat to the air, and basically it combusts with the air, and the exhausted gases are in high temperature and high pressure. So we have the Q in there. But for 5 we have the temperature of 1200 Kelvin. So let's go to the 5 and we can write T5 1200, and we have H5 again and PR5. So H5 is 1277.79, which is H7, and PR5 is 238. So again, now just writing the pressure ratio definitions. So here, 5 to 6, PR5 to PR6 equals P5 to P6. So this is 3. So basically PR6 equals 1/3 times PR5 . And from here, table, we can find H6 and H6, H8. So 5, 6, 7, and 8. So now we have 1, 2, 3, 4, 5, 6, 7, 8. So we have the H, and we can calculate the thermal efficiency and so on. But first, go back to the question to see what we were asked for. Back work ratio. So what is the definition of back work ratio? Just anyone, if you have in your mind. So work ratio, basically. So what types of works we have in our cycle? So we have compression, we have expansion, okay? So work ratio means the back work ratio means the the amount of work that we get from the grid or whatever, to the amount of work that we give. So basically, or amount of work that we consume in the cycle to the amount of work that we produce. Basically means that back work is the work of compressor over the work of turbine. So work of compressor, this is a specific work. It means that we don't need to multiply m dot or whatever, it's per kilogram. So we deal just with H. So basically the work for the compressor, 1, is basically H2 minus H1, okay? So the work of compressor in is H2 minus H1 plus H4 minus H3. So in this case, because the compression ratio is the same, so H4 minus H3 equals H2 minus H1, so we can write 2 times H2 minus H1, and turbine out, the same thing, 2 times here H5 minus H6. So we have the values for H's, right? So we can say we come up with these values, 277.68 over 568 0.44, which is 49.3%.
The work of the turbine, sorry, this question's different than the work of the turbine is 660.
Yeah, I think there's a difference between this and,
one's a little
right?
different, yeah. This is not ideal, the one
Yeah.
that they do, but the table values are the same.
That one sheet is not ideal.
Okay, so can you give me the value for this?
Yeah, for just work turbine,
Mm-hmm.
it's, so for the compressor, it's 222.14,
Mm-hmm.
and for the turbine, it's 662.
52?
62.86.
Right, like this?
Yeah.
Okay. And it comes as like 35 something?
Yeah, 33.5.
33.5, yeah. Percent or 0.33. So this is for the backwork ratio, and we were asked also for thermal efficiency. So basically, eta thermal. So thermal efficiency or energy efficiency, which is a better definition, the general definition for energy efficiency or thermal efficiency is useful energy output over energy input. So what you do, you just don't write like, okay, you may memorize this. Okay, we will come to this. But I want to give you the whole concept. So you draw a line around your whole system and you see what flows of energy coming in and going out. So you make this big system as what I told you, like a box with inputs and outputs. And you consider just the useful outputs as the numerator and all the inputs, energy flows inputs, in the denominator. So here, what is the main purpose of this Brayton cycle? Is power generation, right? So what is the net power generation? So we can write, yes, the output power generation is work of the turbines, so 2 turbines. But we can deduct the work of compressors, or we can write like the work of turbines are outputs and work of compressors are inputs, or we can combine them or deduct that as Wn. So Wn is work of turbines minus work of compressor. So this is the main output. And where is the input of the cycle? So we have a combustion chamber. As I told you, we have a Qin. So that input, which comes from fuel, usually it's natural gas, is given to the system. And also a reheater, which also burns some fuel. So here we have reheater and Qin. So basically the Qin, the very simplified form of Qin can be written as H5 minus H6, okay? But it's not the case in real, so it's like the equation can't be that simple. But in your case, just write H5 minus H6, and for the reheat, also H7 minus H6. So what we have here, let me just clean this area. We have Wn and Qn we have the H. So can you tell me the number for Qn?
1197.96.
And for Wn, W net
440.72.
0.7, right?
2.
Okay. So we have W net and we have Qn. Which is 440.72 over 1197.96, which is 36 point something?
Yeah, 36.8.
0.8%. So usually in a 2-stage Brayton cycle, we have an efficiency of between 30 and 40%. So just keep that in your mind. So basically when you have without regeneration, without heat recovery. So in the next case, we will go through a regenerative system. But in this case, we have usually the thermal efficiency of between 30 and 40%. So here, 36.8. Any question? Okay, regenerative. So in a regenerative case of Brayton cycle, we have the same thing from 1 to 4, the same thing as before, and we have also the same thing from 6 to 9, here 9 because we add one step. Means that we keep this 6 as 1200 Kelvin, and we have the 4 with the same temperature as it was before. The only difference is that the air that enters the combustion chamber 5 is in a higher temperature than before. Means, so when you want to heat up airflow from a higher temperature to 1200 Kelvin, imagine before it was 400 degree, Now it's 5 with 700 degree. So when you want to heat up from 700 degree to 1200 degree, what does it mean? It means that you need less fuel. So basically, you use less amount of fuel for that heat transfer. So this heat recovery is beneficial in economic aspects and also energetic aspect because you consume less fuel and also you increase your efficiency, which will be shown. So basically here 5 is in a higher temperature. So how we increase this temperature? From the exhaust gases that goes out of the second stage of the turbine in 9. So based on design of the system and the temperature of 9, we can do this, not every time. But in this case, let's see. So we have here, for the regenerative case, Q regeneration. So this is the Q regeneration, means the Q that we save. So basically the amount of energy compared to the previous case that we save is H5 minus H4. So previously we wanted to go from 4 to 6 directly. Now we go from 5 to 6. So the amount that we save is 5 to 4. It's like 4, 5, 6. Right? We wanted to go to here. Now we go from 5 to 6. So this is the amount that we save. Right? So basically Q regeneration means the amount of energy that we save, which is H5 minus H4. But we don't know 5. But we have effectiveness of 75%. So if we write the definition of effectiveness, so for any heat exchange process, in any case, in thermal engineering, in heat transfer or thermodynamics, effectiveness means the actual heat transfer to the maximum heat can be transferred theoretically. So what is the maximum heat can be transferred theoretically here? So we have a hot flow of 9, okay? So we want to gain some heat from 9, some energy from the flow of 9 and give it to 4. 4 is the coldest stream. 9 is the hottest stream. So basically the difference between 9 and 4 is the maximum that theoretically can be gained. Means H9 here minus H4. This is the maximum, or we can put it that way. The difference between the hottest flow and the coldest flow in a heat exchange process, with which we have 4 flows here, 9, 10, 5, and 4. So this is the dominator, and the actual heat transfer, we have H5 minus H4. So H5 minus H4 is what we are looking for, right? So if we multiply epsilon times H9 minus H4 equals H5 minus H4, right? So we have H9. Why we have H9? So H9, remember I told you that from 6, which is 1200 degree, we have the same expansion ratio and we have the same values. So basically 6 to 7, 8, we can get 9, which is the same as 8 here. Because 6 here, like we have 1200, and the process goes its way to 8. So we had H8 here. Okay, 946.36. So this H9 here equals to the H8 old, the H8 of that we calculated. We can also calculate it again, like we have 1200 here, just put the work pressure ratio and find 7 and find 8 and 9. So we have this, we have 4.75 times, can you give me the value?
So for Q reach generator, it's 401.33. Oh, sorry for that.
So yeah, can you just,
Sorry for that.
so
946.
946, yeah.
0.36
Mm-hmm.
minus 411.26.
Okay, thanks. Equals,
401.33.
yeah, 401.33 kilojoule per kilogram. So Q regeneration we found out as 401.3 kilojoule per kilogram. So what we were asked for? So the thermal efficiency in the case that we have regenerator, okay. So W net is the same. Why it's the same? Because I told you that from 1 to 4 and from 6 to 9, it's the same as we had before. So the work produced and work consumed are the same. So WT minus W compressor, W net is the same as we had. So we have W net. But what about Q in this time? So Q in this time is not the same as before. So we had the Q in. So basically Q in new I write equals Q in old minus Q regeneration. Small q's are better because it's specific. Okay. Do you understand this? If all of you understand this equation, that's great. So why I wrote Q in new equals Q in old minus Q regeneration. So Q regeneration is the amount of heat that we saved in the second type, in the regenerative type. So we deduct that amount as the whole energy that entered into our system. So we have thermal efficiency here, W net over Q in new or Q in regenerative equals can you give me the value?
So W net is 440.72 and Q in is 796.63. 63, sorry.
Thanks. Yes.
And you get 55.3%.
So thermal efficiency in this case, 55.3%. So you see 0.3% regenerative no regeneration. How much? Almost 20% difference. So the heat that we recovered caused a 20%, almost 20% increase in the thermal efficiency. Why? Because we consume less fuel and the Q input lowers, and we have higher thermal efficiency. It won't go higher than 60% by any mean of heat recovery and stage of turbines and compressor. So basically, if you come up with 80% efficiency, it's wrong. Like basically, it's something with regeneration, it's something between 40 and 60%. Usual cases are around 50%. Questions about any aspect of the cycle, any state point, regeneration, effectiveness, and all those things? Okay, so let me just show you okay. So this is the real combustion chamber, and this is the compression stage. Compressor. This is an 120 megawatts Brayton cycle on one shaft. So here, basically, if you can't see in this figure, but here is the turbine, like gas turbine at the end. So you have the compression, like almost 5 meter, 6 meter, and also the turbine for like the same, a bit more, and the combustion chamber from two sides. This is just one side. From the other side, we have another kind of that, and there are some sprays you see here. These are igniters. So basically, that makes ignition and sprays the fuel into the combustion chamber, into that area. And this is also a video by General Electric, if I have the audio.
A lot of gaseous molecules floating all around us. It's great for breathing, and it turns out it's great for getting lights turned on. That's because air, along with abundant natural gas or other fuels, are the ingredients that combine in a gas turbine to spin the generator that produces electric current. If you follow the electricity you use at home or at work back through the power lines to your local power plant, you'll see that the process most likely starts with the work of the gas turbine, the very heart of the power plant. First, air is drawn in through one end of the turbine. In the compressor section of the turbine, all those air molecules are squeezed together, similar to a bicycle pump squeezing air into a tire. As the air is squeezed, it gets hotter and the pressure increases. Next, fuel is injected into the combustor where it mixes with